destroys them. See? They don't survive in an oxidizing atmosphere. So there was a reason to choose a reducing atmosphere. Okay. What happens? A little bit of chemistry. The nature of a chemical reaction. All chemical reactions occur because you put something together under certain conditions, and the conditions are sufficient to produce a product. So something has to change, obviously, right? What are the things that cause the change? Energy is the thing that causes the change. Of course, the nature of the components themselves, whether they can or cannot react, is a critical thing, because some things are prone to reaction by their very nature, other things are not. But they can be made to react under stringent conditions. So conditions mean a lot in chemistry, right? Okay, so you get a reaction, reactants plus energy, and the conditions gives us a product, okay? And of course, there's energy involved there. Energy on both sides. The energy is balanced, of course, in the outcome, because you can't, by law of thermodynamics, you can't lose or gain the energy. It's got to be balanced off. Okay, the requirements for the products to form must be greater than what the energy of the product's going to be. In other words, you got to have more energy, enough to start with, if you're going to get something coming out that's going to use up that energy, right? How can you get the energy being used up that's not available to start with? So you got to have more going in, okay? That's the whole thing. So there are two ways of recognizing this. The energy of the products minus a reactants called delta E is released. That means you had more than you needed, it came out, called exothermic or exergonic, depending upon if you're looking at it from a standpoint of heat transfer, or if you're looking at it as a standpoint of free energy transfer, okay? Same thing. Then the energy of the products minus the energy of reactants, if it's a positive delta E, that means it's absorbed. Well, that meant what? You didn't have more to start with, okay? You had less to start with. That's why it's positive, okay? Right? Because it's the reactants minus the products minus the reactants. So if that becomes positive, that meant your product energy was greater than your reactant energy. Could that have occurred instantaneously? No. Why? You need an input of energy to overcome that condition. Okay? Energy has to be inputted. Okay? That's called endothermic or endogonic, as again, is plenty. Two primary factors, thermodynamics and kinetics. Thermodynamics is the energy requirement, kinetics is the speed at which the process takes place. If you can't satisfy those two factors, you can't have a chemical reaction. Okay? That's very, very fundamental. All right. So let's see what happens if we apply these principles to Stanley Miller's stuff. Here's Stanley Miller's results. That's only part of it. But I'm just taking the most important ones, the ones that are in greatest amount that were produced in his experiments, okay? He had an amount of hydrogen cyanide, 0.163 moles, and I'll explain to you what that means in a minute. Here's a formic acid, 0.233, a little bit less than the hydrogen cyanide. Here's a glycine, that's the simplest amino acid. He produced that, okay? It's 0.0063, much less than these two. And then here's a alanine, which is a modified amino acid. It's even smaller than the glycine. So he did get a few amino acids, but they're in lower concentration. Got a lot of hydrogen cyanide, relatively speaking, but he got a lot more of this acid than these amino acids. Very important to recognize that, okay? Now, HCN is not a factor because why? It's not even involved in the peptide bond mechanism under the conditions that were being assumed. You may look at other conditions in which HCN maybe could have a role, but it wouldn't be these conditions, okay? So HCN is not a controlling factor, okay? The pH is not alkaline, the pH is acidic, so that removes HCN as a factor. The formic acid is a primary factor. Why? It can react with amino acids in this environment. Which one do we have more of? Formic acid or amino acid? Here's formic acid, 00233, and here's the greatest amount of the amino acid, 00063. Right? 1 decimal place smaller than this. Now, a mole is a quantity of substance that would be available to produce a what's called an Avogadro's number of particles, a 0.6 trillion. Okay, and every substance in chemistry is gauged in quantities by moles. So we call them gram moles because you measure it in relative gram amounts. Okay. Anyway, the important thing is they show you the relative amounts, and that's what we're concerned about. All right. All right. So formic acid is important. The amount of formic acid is a greater excess than the amino acid. So what do we expect? If the formic acid can react with amino acid, what's going to happen? It's going to react. Will there be any amino acid left? No. How are you going to get peptide bonds? You can't. How are you going to get proteins? You can't. Nothing can happen because the amino acid's removed. Here's a reaction. Formic acid and glycine. All right? It reacts. Here's the formulated product, as we call it. This bond across here is called the peptide. Well, it's a formulated bond in this case, but it would be a peptide bond if there were 2 amino acids. It's very similar. And an acid form of hydrogen in water called hydronium ion. All right, that's all fine. The thermochemistry says the sum of the reactant bond energies on this side minus the product bond energies on this side is a negative 10 kilocalories, a measure of energy. Negative 10 kilocalories. Okay, so the energy change is negative. Thermodynamically, what did we say? It's exothermic. As I said before on the previous slide, remember? What does that mean? That means it can happen, right?
So they lied? So they lied in the experiment?
Oh no, they didn't lie. I'm just showing you that these results, if you put chemistry to their results, what would really happen? Okay? They didn't do this. Okay. You know, they ignored this. Okay? I'm just showing you, if you seriously analyze this, this is what you get. Okay? So that looks favorable. Well, it is favorable. In fact, let's look at this thing. It's exothermic, it will occur.